Hi all, welcome to part 11 of the video lecture on counters. So in part 10 we saw that implementation of something called binary up counter. So the general way, so how we can implement any n bit up counter without depending on that state table. So that implementation, state table based implementation is what we saw in part 9, and then we generalize it to any case. I hope you remember. And from that understanding is needed to understand this. So here we are going to see something called binary up and down counter. So which can do both binary up operation as well as down operation depending on some control line. So what we saw already is up counter, and we made an observation. Now what about a down counter, right? What kind of observation we can have about a down counter? It's what we will see. And then up and down counter together, that implementation we will see. Okay, yeah. So hope you remember, like if I am having some k bit up counter. See, what are all the observation we made? We implemented using k flip-flops, right? So I can say that k flip-flops, it can be t or jk, both we saw. D also you can try it out. Okay, so let me write like that. So k flip-flops are needed. So it's basically a k bit register, and for each flip-flop, suppose I am using t flip-flop for simplicity, or jk, either in toggle and in no change mode is what we needed basically for counting. Okay, so if that is the case, let the bits are like a k minus 1, a k minus 2, etc. a 2, a1, a0. So these are all the bits. So each bit how it is to be changed is determined by the corresponding flip-flop, like a flip-flop. So this transition of this bit will be determined by flip-flop 0, and this will be determined by flip-flop 1, etc. The kth bit, that is will be determined by flip-flop k minus 1. So this is a basic idea. Now how this transition will be done by like flip-flop 0. Okay, so you know that for the least significant bit it will toggle always. Whatever be your binary, it will toggle always, right? So what we so is like if it is, so TA0 corresponds to the toggle or not toggle, the input of the flip-flop 0, and we made it just 1, saying that always toggle, right? Always toggle. Similarly, when it comes to TA1, we saw that it is something A0. And TA2 is something like so how we are obtaining it, please watch previous video. A0 A1 and TA3, it is nothing but A2 A1 A0. And so what kind of observation we made? Whenever all the least significant bits following it are all 1, that particular bit has to be toggled. So that kind of an observation we have. And in general, TA minus 1 will be the AND operation of AK minus 2, AK minus 3 dot etc. a2 dot a1 dot a0, like that. Okay, and for example, if you are looking at a 4-bit counter, so 1 1 0 0, or maybe let's take the toggle case, something like so we saw in the previous video 0 1 0 0 1 1, like that. So what is the next state? You know, as this bit should toggle always, so this bit will toggle always. Okay, so this will toggle always. And now what about this bit? So this bit is determined by A0. A0 bit is 1. So that is why I want to toggle this. Okay, now A0 and A1 both are 1. That is why TA2 will be in toggle mode, and this will be toggled to 1. Okay, now if we are looking at the bits following it, they are all not 1. So that I will retain this bit as it is. Okay, so 0 0 1 1, that is 3. Following that, what I am having is 4. So like that. Now what about the down counting? So that is my question. What about the down counting? Down counting, the opposite thing should happen. Like for at any time, suppose it is the current state, the next state has to be 0 0 1 1. Now the question is how you will achieve this opposite thing. Okay, so as usual, the least significant bit that should be toggled always. Okay, now what about the next bit? The next bit will toggle only when the bits following it are all 0. Here the rule is, for up counting, the rule is the bits following that particular bit, they should all 1. That will let that particular bit toggle. Okay, so here the bits following this particular bit should be all 0, then only this bit will be solved. So if you are looking at this bit this particular bit, whether it is to be toggled or not, it is to be toggled because all the bits following it are all 0. Similarly, what about this? That is to be toggled because all bits following it are all 0. That is why. Now if you are looking at this bit, there is no toggle because the bits following it are all not 0, right? So that 0 case is what we need. So so this is for the up counter, the default counter we saw. Now when it comes to down counter, As usual, this TA0 will be 1 because that bit should be toggled always. Now what about your TA1, and this will be your A0 complement. You should not take A0 because 0 is now asking that particular bit to be toggled. Okay, so A0 complement. So you know every flip flop A0 and A0 complement both are available, right? So from that you can make the connection now. Similarly, TA2 will be A1 complement dot A0 complement. So you take that complement input and accordingly you do that. Okay, so similarly the last bit. So this is your idea behind the down counting. If you want, you can implement the down counter easily like this, right? Now let's see the circuit which can do both up counting and down counting together. So you may be using a some kind of controller input. So a synchronous count down. So here we are talking about the down counting or count down counter. Binary counter goes through the binary states in the reverse order, like starting from, if it is a 4-bit counter, from 15 it will go to 0, right? And again back to 15 and I mean 441 and repeat. So it is possible to design a countdown counter in usual manner, but the result is predictable by inspection of the downward binary count. You know, usual manner is the state table method, but you know the problem, right? For bigger some bits and all, it will be difficult to do it, right? It's a tedious thing. So we can have some observation, right? Inspection of the downward binary count, and we had that count. So what kind of observation we made? If you are looking at the least significant bit, that is always complemented in each and every pulse, okay? And the other bits, a bit in any other position is complemented only if, okay, complemented if so this is a condition, only this condition, in that case only that particular bit will be complemented. So if all lower significant bits are equal to 0, that make the, I mean if I want to know whether the kth bit is to be toggled or not, just observe the bits from 0 k minus 1 backward towards 0. So if bits from A0 to ak minus 1, they are all 0, the kth bit will be toggled, otherwise it will not be. If any one of the bit is 1, it will not be toggled. For example, the same example we saw, like after 4 you should get 1, and you know this bit is toggled because it is a least significant bit. This bit is also toggled because the bit following it is 0, and this bit also toggles because all the bits following it are 0. That is why now this bit, you know, this remains same because the bits following it are all not 0. Is that idea clear? Okay, let me remove this looking complex. So you can see that the least significant is always complemented. The second bit is complemented because the first bit is 0. The third bit is complemented because the last 2 bits are 0. But fourth bit is not changed because all lower significant bits are not equal to 0. Not is here. Okay, fine. Then binary up and down counter. A countdown counter may be considered as before, like what we saw in previous part of the video, except that the inputs and the AND gates must come from the complemented output. Like previously it was like A0 dot A1. Now it should be complement, like TA1 should be A0 complement, TA2 should be A0 complement dot A1 complement, like that, instead of the normal input of the previous. So the two operations can be combined in one circuit to form a counter capable of counting either up or down depending on what we need, right? So our need, we have to express through the control line. Accordingly the counter will do for us, right? The circuit of an up down counter, binary counter using T flip flop is shown in the next slide. We will see that it has an up control, okay, and a down control. So you can control it using a single control line also, but here it is implemented in a more general way. We will see sometimes we want to we may enable both, and at that time it will give some priority for this up counting, like that, okay. So it's a more general implementation, so that's why it's using two different control input, a up count control and a down control, okay. Whenever this up is 1, you know you want the circuit to behave like an up counter, right? It counts up since the T inputs receive their signals from the values of the previous input, and okay, that we will see the circuit, you know how that up counter is working and that AND operation of previous bits, and that kind of logic we will implement corresponding to the case when up is equal to 1. Similarly, when down is equal to 1, and whenever this down is equal to 1, you have to ensure that the up is 0. So that clearly says that I don't want this up operation, I want only the down operation, and that time it will do that count down. Because because we made connection from the complemented output to the previous output, and that we will see. So when the up and down, sometimes both input you will be, because two inputs are there, it's the combinations are like up and down, so both of them can be 0, 0, 1, 1 0 and 1 1. So whenever I am making both of them are 0, I don't want, right? So I just want to return the last information. I neither want to count up or count down, right? So here I want to count down explicitly, because down bit is 1, up bit is 0. So here I want to count up. Okay, now this is the tricky thing, like when someone turn on both, I want to do up counting and down counting, it will give a default priority to up counting. So this will also corresponds to count up. Okay, so that is how the circuit is designed. So this is something I taken from the textbook. We can have alternate design also, but this is something more general case, right? When the up and down both are 0, the circuit not change the state, so it will retain the last information it is having. Okay, now when up and down both are 1, the circuit counts up. That means it's giving a priority for up counting over down counting. So this set of condition ensure that the only one operation is performed at any time, right? So 4 cases. Right, no, none of the cases for 2 different activity, only one thing is happening at a time. So not that the up input has some priority over down input, so that is by default the circuit is implemented like that. Okay, now this is a typical diagram. Okay, and you can see that, so this is a logic we implemented already for up counting, like what we taken is like this A0 we are taking here, right? So here you can see that, so this is this in output is actually A0, not only A0 dot up. So I want I want to ensure that this up control line, so that is coming from here, it should be 1, and also this A0 should be 1 to have the next count. Okay, now if you are looking at this one of the input is coming as A0 complement, so this is actually A0 complement and down, right? The down control line is equal to 1, saying that I want to count down, and also that toggling of that particular next bit will happen only if all the lower order bits are 1. In case of up counting, all the lower order bits are 0 in case of down counting, and down counting, that is why 0 I am taking its complement, so that the lower order bits are 0, the complement will be giving me a 1. Okay, so like that. So any one of them should let the, so either up counting or down counting, any one of this output line will be 1, right? So at any time, or either this AND gate 1 or AND gate 2 will give you 1, that is for sure, because if A0 is 1, this will give you 1, and that time this will be giving you a 0 as the output. Okay, so that is for sure. So any one of them will be 1 at any time, so that this OR operation, this will give you a 1. If either up or down counting I want, accordingly that bit will be changed, right? So how to have that change and all, that is depends on whether the least significant bits are all 0 or 1. Up counting, you know, I am not repeating again and again. Okay, so that circuit we are just generalizing. Now what about the next bit? This one, up counting corresponds to the AND operation of all the previous bit, like A1 dot A0 dot this up also, because that control line should be 1 by default for making that up counting possible. So that says that the up counting is needed, right? So and this A0 dot up you are getting through this line, and this A1 I am taking addition. But if you are looking at this output, you can see that here it is A0 complement dot A1 complement dot down. So here A0 complement dot A1 complement I am getting from here, A1, sorry, A0 and down, A1 complement I am getting from here. So like that. Okay, so now you know, right? Similarly the last one, the AND operation of all the bits following it, AND operation of the all the and complements of all the bits following it, like they all should be 0 for making that down counting possible. So this is how you can implement the circuit. Now tell me if the last case, we can just have a look into the last case, like suppose I am giving this both up is equal to 1 and down is equal to 1, what will happen? I said like there is a default priority that is given to up counting over down counting. Let's see whether it is happening. So this bit is 1. Okay, fine. Now what about this one? When I am doing this, I am applying this negation, and down bit I am not taking directly, down bit I am taking as through the negation of the up bit, so that if this bit is 1, this negation will give you a 0, and even though I am making the down bit as 1, the output of this AND gate will be 0, so that down operation will not be enabled. So down operation we are not directly connecting to all the AND gates, right? We will connect it through some kind of masking, like through that AND gate, and where the other input is coming from up. So if due to any reason the up count is 1 and down count also 1, the up count negation that will give you 0, so that the down count is not not at all coming out from the circuit. So it will simply give 0 as output, so that the down counting is not enabled, it will do only up counting. And in worst case, if both are 0 0 means all the AND gates will give you 0, so that all the flip flops will retain the last information. There is no toggling at all. Okay, now it is clear, right? All the 4 cases you can explain now. So it's a very simple circuit, but you should understand how it is working. Then only you can draw it. And also for the exam, just try to practice this kind of diagrams to draw in a neat way. Okay, so if you're drawing in your own way, it may make things complex. Okay, so and also write that expressions very clearly. So the important thing is more than this drawing. So you have to say that what is the so if I'm saying like that, this is your TA0, right? This is your TA1, and you know that this TA0 is 1, whether it is up counting or down counting. If I want some sort of counting, this has to be 1. Otherwise, up and down both I am giving 0, this will be 0, so that it will retain the last information. So up or down counting both the time, this is getting 1. And TA1 is now this OR operation is doing it like either it is like A0 dot up. Okay, so that means I want to perform up counting, so that this depends on this bit A0 whether this is to be toggled or not. Or another case is like A0 complement dot down. Okay, like that. So writing this expression is equally important, even though your circuit looks messy. By looking at this equations and all, you will get the marks in the university exam. So that is why I'm saying it repeatedly. So here this will be A1 dot A0 dot up. This is one case. Or A1 complement dot A2 complement dot down. So this is another case. Any one of them. So if this is 1, this will make up counting. This corresponds to down counting. And so all of these two is what is applied to TA2. So accordingly it will do that. Okay. Yeah. Thanks for watching. We will see few more variations of the synchronous counting in the next video.